what I have done here with this section is I have basically copied for you what's out of the book, just so you can make notes on the side. Basically what I'm going to do is I'm going to go through this section of the book, sort of make notes on my version of what you have, and you should do the same on your paper. Okay? So I've just reproduced the graphs in your book there for you to write. So it says, in the last chapter we found velocities from displacement time graphs by taking slopes at given time. You guys should have done that in grade 10 and grade 11. Taking the slopes of displacement time graphs and to find velocities. In this chapter we'll use these values to create velocity time graphs and analyze them using three primary analysis methods for graphs learned in the last chapter. So let's begin with constant velocity graphs. A motorcycle is traveling along a straight, level road path marked at 40 meters, 100 meters, and 160 meters at the times you can read on the graph in figure 2.18. This DT graph is a straight line. This one right here. And because it's a straight line, you know that the slope is, or the velocity is, constant, right? And in fact, what they've done here is they've shown the slope right there is 20, the slope right there is 20, the slope right there is 20. It's constant, right? You can write right in there, constant velocity. They found those three slopes, and they've recorded those in this table over here, right? 20, 20, 20. This is what kind of graph right here? This is a velocity time graph. Why is it flat like that? Constant velocity. Okay. So below the graphs in your book, it says, reading the graph in figure 2.2, the units on the y-axis are meters per second, which indicates velocity. Since you're given reading a given velocity at a given time, reading this graph allows you to find instantaneous velocities, right? You're reading this right here. How fast is it going at 2 seconds? 20. How fast is it going at 6 seconds? 20. It's constant. Finding the slope of the graph. What's the slope of this graph going to give you? Well, numerically, the slope is going to give you 0. 0 what? Meters per second squared. The acceleration is 0, which means it's doing what? Constant velocity, right? All tying together, right? All easy stuff, I'm hoping. Excellent. Top of page 39. The slope calculation produces a value of 0 with units of meters per second squared. This quantity is the change of velocity over a given time period. We can see that if an object has a constant velocity, its acceleration must be 0. The process of changing the velocity is called acceleration, and this leads us to that A equals delta V over delta T. Now, I think I have it on the next slide, but you guys have it on the same page. Do you have this on the same page? You do, right? Okay, so if we were to find the area, and we did this a while back, that first week or so, right? Right? If we were to find that area, and we said the time here was 5, what would be the area under the graph? Well, it would be base of 5, height of 20, 100 what? Meters, right? The area covered in those 5 seconds is 100 meters. If you look back at the displacement time graph, 5 seconds, what do you know? 100. Should it be? Absolutely, it should be. Okay, just a refresher of all these things. That's what they're talking about there in that first little bit. If it's below, like this, then that's going to be, this is again 5 seconds, and this is minus 15. So the area of the displacement is 5 times minus 15, which is 30, 60 minus 75 meters. This is if it's traveling at a constant minus 15. I took that flow chart at the bottom there. Basically, this is sort of that stuff that I gave you at the start where we had those 2 columns, right? 3 graph analysis techniques for VT graphs. So if you have a VT graph, what do you read right off it? You read meters per second or instantaneous velocity. If you're taking the slope, well, that's going to be in meters per second squared, which is acceleration. And if you're finding the area, you're measuring that in meters, which is displacement. Again, this takes the place of that right-hand column in that summary sheet that I gave you, right? A while back. Now, page 40 shows us graphs with change in velocity. Is it going to get more complicated here? Okay. Zach wants me to make things more challenging. You can have a discussion with him later. Huh. You're not making yourself very popular, Zach. That's my job. Graphs with change in velocity. On a performance test, the Honda Civic produced the DT graph in figure 2.5a. As you saw in chapter 1, a curved DT graph means the velocity is changing. We know that. Finding the slope of this graph at 4 different times gives the velocities as shown in figure 2.5b. Plotting these points gives the VT graph in 2.5c. So what they're saying is, you'll notice here I've got a small little line right there, small line there, small line there, small line there. Those are all known as what? Tangent lines. Exactly right. So they took tangent lines, they found the slope of them, and they found the slopes to be 0, 6, 12, and 18, right? 0, 6 up over 1 is 6, 12 up over 1 is 12, 18 up over 1 is 18. They took those velocities from the tangent lines and they plotted them. 0 at 0, 1.5 and 6, 3 and 12, 4.5 and 18. And they got a velocity time graph that is like that. What does this mean? Or certainly increasing velocity, right? Someone said constant acceleration. How do you know it's constant acceleration? And it's in a straight line though, right? Yeah. 4 meters per second squared? Okay, so increasing velocity, good. Finding the slope of the graph. 2.5c shows a steadily increasing velocity. If the velocity increases, the object is accelerating. Finding acceleration, find the slope of the VT graph. As Stephen pointed out, we would find the slope of this, right? And I could just take like something like 18 minus, I guess, 0 over 4.5 minus 0. 18 over 4.5 is 4, is it not? Yeah. 4 meters per second squared. Now.
It's 4.5 minus what?
0.
4.5 minus 0?
Yeah, because these are the x values here, right? 4.5 and 0.
Okay, cool.
Now, they don't show it there, but what would the acceleration time graph look like for this? Have you got room for it?
Line, like,
Yeah, it'd be a... When you say straight, you really meant flat.
horizontal.
Yes, I know.
I don't know what's the gesture.
I know. I can see it out of the corner of my eye. When students often say straight, they really mean flat.
Sweet.
I don't know why, but yeah.
Nice, you know.
Yeah, it happens. Okay, good. Now, what about the area? Is the area, again, equal to the displacement? And they go through that there at the bottom of page 40. Find the area under the graph. The area under the graph in figure 2.6 is a triangle. The area of a triangle is base times half the base times the height. By substituting values and units from the graph into the equation, we obtain half the velocity times the time. And then they give you a displacement for at 3.5 seconds, right? Which is this one right here. So it's going to be, I should have left myself room here. Rats. And I probably should have given you that graph at the bottom of page 40 there, right? Well, let's squeeze it in right here. So that's going to be 1/2 the base, 3.5, and the height was 14 is what it tells me. Right? 24.5. So at 3.5 seconds, it should have traveled 24.5. 3.5 seconds? Pretty close, right? That's what it should be. Again, just reinforcing some of these concepts.
Is that 14?
Yep. 14. I'm just going by what's at the bottom of page 40 there.
Oh, they
Yeah.
show you on there?
Yeah,
Oh, they do.
they show you. I didn't include that graph on my thing. I should have. Probably say that every year. Okay.
No, it makes sense.
The next one is where things get a little bit hairy. Okay, so I've got here page 41, working with negative motion. Repeating the test drive in a westward direction, produce the VT graph in 2.7, calculate the acceleration, and reconstruct the DT graph. This is the something new, finally. So if you've been nodding off, time to wakey wakey. Okay? Calculate the acceleration and reconstruct the DT graph. So, in the standard reference frame, westward is negative, hence the velocity is negative, but that does not change the process finding slope. Figure 2.7, the slope of the VT graph gives an acceleration of -4, or 4 meters per second squared west. Although the acceleration turns out to be negative, it's in the same direction as the velocity, therefore the object is speeding up. So this one right here has a slope of, see how it's -8 and 2? Right? So the slope here is -8 over 2, or -4 meters per second squared. But because it's negative doesn't mean it's slowing down, because the velocity is also negative. And when they're the same, it's going to be speeding up.
Then you still keep it as -4 then?
Oh yeah, it just means that it's to the left, that's all. You can be negative and to the left and still speeding up, Steve. Okay, that was relatively easy. The hard part is finding the displacement. Okay, so how do I get a graph? Like I could say to you, here's a velocity time graph, tell me where it's at 3 seconds. You could do that, right? But can you make me a graph? Because now I'm really asking for multiple displacements. And if you stop and you think about it, it's really not that hard. It's asking you to do the same thing over and over again and then plot those values. That's all I'm really saying. So let's go through that. So what is the displacement we're looking for? We're creating a displacement time graph. So on this graph right here at 1.5 seconds, what is the displacement? Well, they've conveniently got it down here in the left-hand corner for you. So at 1.5 seconds, this little triangle here that's labeled with a A, blue A, you're looking on, I'm not sure which page you're on, but I'm on page 41, and you're at the one that's labeled figure 2.8. See it? Okay, good. Thank you for asking. So the base is from 0 to 1.5, so it's 1/2 times 1.5, and the height is -6 because it goes down to -6. So the displacement after 1.5 seconds is -4.5. See that right there? Then we're going to do the same thing for 3 seconds. I'm going to do it in red right here. Oh, I guess it's blue, sorry. Let's do red. Now, this is triangle A plus B. This red triangle here, the bigger one. Okay? It now has a base of 3. It has a height of -12 according to this, giving me a displacement of -18. Half of 3 times -12 is 18. Do the same thing for A plus B plus C. Here in black. Now it's red again. We're finding the third displacement of triangle A plus B plus C. All the way from 0 to 4.5. All the way from 0 down to -18, giving me a displacement of -40.5. I've just found 3 individual displacements at 3 individual times. To construct the DT graph from that, I simply make a graph, exactly. Are you surprised, Jason, that it's curved like this?
No,
You shouldn't be. Why is it curved, Jason?
because straight line on velocity time graph, or
Yeah.
diagonal line, but it's straight on a velocity time graph.
Okay.
It's curved.
Right. Without talking about the graphs, the velocity here is staying the same or increasing? Increasing in a negative sense, right? Just means increasing towards the left, that's all. Increasing in a negative sense because the velocity is increasing, the displacement time graph must be curved. How hard was that? Not particularly. If I'd asked you to do it right at the start, you'd say, I don't know how to do that, right? But all I really did was calculate 3 individual displacements and then do what? Graph them. Not that hard. Okay, awesome. Flip the page. What about when velocity and acceleration have different signs? Okay. This is a position time graph. It is getting flatter, right? See how it's getting flatter? This means that it's doing what? Slowing down, right? Getting flatter, slowing down. So they took individual 3 different tangent lines, found the slope, put those slopes in a chart, right? Here the slope is 30 over 1. Here the slope is 12, 24 over 2. Here the slope is 0. They took those and then they graphed them. There's the 30, there's the 12, and there's the 0. Are you surprised that the velocity time graph is down like that? Yeah? What's surprising about it?
Really, if I look at it more.
You stop and you think about it a bit? Would you say that the slope here is approaching 0? The slope is approaching 0? Would you say here that this is a graph of the slope and that it is also approaching 0?
Yeah, I guess.
Right?
Once it becomes straight or flat,
Then this would have to be 0. Now, here's a bit of an extension thought for you. What if I took this and continued it like that? It would be going left. Would the slope of this gives me the what?
Velocity, yeah.
The slope of the velocity time graph gives me the acceleration. Would you say that it has remained the same, the acceleration?
yes, yeah.
Because it's straight, right? So, I'm talking about the slope. What's the slope right here, Steve? And the same as the slope down here. It would be a negative slope, right?
Yeah.
Okay, so now here's the big challenge question, and if you don't get that, this is fine. What would, if I did this blue bit here, how would I draw the blue portion here as well?
Curve back down. Yeah, they're coming back down.
Kind of like a haystack kind of thing?
Yeah.
Like upside down, like you want me to do this?
Yeah.
You would love a what? You're weird.
goes flat.
What else? Any other options, or do you think that's it?
It goes flat.
You think it stays flat, Riley? Riley thinks it does this. What? I guess the only other thing it could really do, I guess, would be, right? What else could it do?
Oh. Wait, doesn't it have to, does it have to come back to 0 and then keep going the other way? Maybe.
But we're still speeding up, it's not like we're slowing down though.
This shows the velocity approaching 0. This shows what? Slowing down, doesn't it? Right? But once it gets to here, is it still slowing down? Here it's doing what?
Speeding up.
It's speeding up. It's getting more and more, a bigger velocity number just the other way. Okay, so even further, and I don't know if I can't go past the edge, but if I could somehow make that blue line go even farther down, yep, this is all correct, by the way. That's all correct. Yep. In fact, the line would have to get steeper and steeper and steeper, wouldn't it? Yes. I've gone way beyond what I meant to today. Those of you that just tuned out, tune back in. That was a hard discussion right there. Well done. Okay. Go to example 3, one of my favorite ones because it's so goofy in the book. A lot of traveling and ending up nowhere, which is kind of how this lesson feels like some days for me. Not my favorite one. It needs to be a little bit better organized. Okay. Do you see in the book the guy on the bike? I guess it could be female, but I think it looks male. Do you see that it looks like they're climbing a green mountain in the background?
Yes.
You see that? You don't see that on your paper because it just doesn't photocopy through. So if you want to lightly draw it in,
Oh, I made mine look like they're going down and then coming back.
yeah, you can do that. Okay? But it's really not a very good thing to do because what kind of graph is this actually? It's a velocity time graph. So this cyclist is riding up a hill. The cyclist traveling at 20 meters per second arrives at the bottom of the hill, climbs up the hill to a stop, and then comes back down again. Find the total displacement as well as the acceleration for each section. Has some student before you written in the word vertical displacement?
Yeah.
If your textbook doesn't say that, it should. Find the total vertical displacement. Because clearly, if I ride my bike up the hill and I come down the other side, well, I've been displaced horizontally, haven't I? So that's not what I'm talking about. I'm talking about vertical displacement. In other words, I'm just as high up as I was when I started.
Does mine say vertical?
It does. Right, you're good. Okay, so it says right before that, find the total displacement as well as the acceleration for each section. Well, the total displacement is going to be, now let me get rid of that red thing there. I'm interested in displacement from a velocity time graph. How do I find that? Area. So area of part A is going to be from 0 to 4, 1/2 the base, and the height is 20. Half of 4 is 2 times 20 is 40. In blue, the area B a 1/2 base times height.
It's just divided by the time.
Yeah. Yeah, that's way fancier, times by a half. Who do you think you are, Mr. Bennett? Mr. Fancy multiply by a fraction guy? Yeah, I'm basically Millikan up here, yeah. Hey, I don't go and just throw data out and, bribe my research assistant by offering him a PhD and taking all the credit for his work.
Read us the whole paper and threw out lots of information.
Is that kind of a round thing to do, Millikan? Like he basically said to his research assistant, hey, I'll take all your credit and I'll just sign off on your PhD. Is that a good deal? Come on.
I was the assistant and I kept trying to...
And? Harvey Fletcher, yeah. And then there's Millikan's wife.
And then who was right?
Yeah.
Aaron's was Harvey.
Okay, back to our problem here. We are going to be, from 4 to 8 is a distance of 4 again, and the height goes all the way down to minus 20. So it's not surprising that the displacement on the other side of the hill is minus 40, giving us a total displacement of 0.
Oh, negative 20. I was negative 2. You
Right.
stop my crap.
I get some bad rating. The total vertical displacement is 0. It's just displacement measured in the vertical sense, right? Now, what would you say about the acceleration here? Because that's the slope, right? What would you say about that acceleration? Would you say that it's constant acceleration? How can it be constant if he's slowing down on the way up and speeding up on the way down, Mr. Madden? No, it's not. It is constant. In fact, the slope of that line is, it's on the next page there, the slope of that line is actually minus 5. He's slowing down at a rate of minus 5 meters per second squared on the way up.
Where does it even say that?
I just found the slope.
Where? Oh, you just did it?
Well, it's on page 44.
Wow, that's not helping anybody.
No, well, it's not hard to figure out, is it?
I don't know.
The slope of that would be, I'm going down 20 and over 4, is it not?
That's for just like the second part of it? you mean?
Yeah, they want us to find the acceleration. He's slowing down, the guy on the bike is slowing down, going up the hill at the same rate that he's, no, I'll say it again. He's slowing down on the way up the hill at the same rate that he is
Speeding up on the way down.
speeding up on the way down. In other words, the angle of the hill up is quite likely, in fact, it's one of those ridiculous triangle hills that's completely pointed at the top. That no one ever rides. Okay. Let's go to the bottom of the flow trader. I'm going to be quiet real soon.
I'll be like,
It's going to be real quiet real soon. Information obtained from a VT graph. I'm going to complete this chart and then I'm going to give you some time to work. I'll come around and help. So if you've got a VT graph, what do you read from a VT graph? Instantaneous velocity. If you've got a VT graph and you're reading slope, well that, my friends, is acceleration, as they say in Francais. And if you use 2 points, well then it's average acceleration. And if you only use 1 point, which means really you are drawing a tangent, well then you're talking about instantaneous acceleration, exactly. And if you find the area, well then you're talking about displacement. And the only way to get average velocity is to take area over time. Really what I've done is, do you remember those probably about 2 weeks or so, there was 2 books about a bunch of graphs, and then at the very end was those 2 columns in grade 11? If I showed it to you, so yeah, right? Basically that's what I just did in about 35 minutes, what we did, so it took like about 4 or 5 days. As sort of a refresher. Okay? Okay.
Oh, wait.
Let's practice a little. On page 46, on you didn't do the project or no?
We got 4 minutes.
yeah, Milliken's like the most important person ever.
I definitely pumped up his net worth.
Milliken can carry a world.
Yeah, Tesla man. I don't know about Milliken. He was a cheater.
What?
He was a scientific cheater.
Oh,
On page 46, there are questions 1 to 4, and on page 69, there are questions. And if I'm not mistaken, the handout that I gave you, I took page 69 and I reproduced the graph so that you can work on them and not draw on my textbook. Page 69. This is these are those questions at the end of the chapter. Okay? Now, let's talk about page 46, number 1, because it always gives, you know what? Number 1 is always giving me grief. I'm just getting rid of it. Just start with number 2. It always gives me grief. I'm just getting rid of it. It's not
So we're
worth it.
doing all those questions then?
I want you to start on 2A. Okay? Do 2A and 3 right away. Do 2A right away. We're going to check it, and then I'm going to show you how to do 3. Go. Find a fresh sheet of loose leaf and go on number 2. Let's look at number 2. Draw a representative VT graph showing uniform motion forward. All they want you to do is draw a little sketch. This is, again, we're doing VT. So for everyone, you start by doing that. And then I want uniform motion forward. Uniform motion means moving at a constant rate. So what's constant velocity look like? Not straight.
Like flat.
That's all they want. 2A. Uniform motion backward.
Same thing, except in the
The
negative.
negative stuff?
Like that? Speeding up forward. Yeah, and it makes that sound effect too. Speeding up forward. I think Hannah's implying, I think she's trying to say this.
Yes.
Excellent.
You can just look at it, it'll let you get it free.
You know what? You know cheat, Risky? Thank you.
We're cheating right now.
Are we cheating?
Milliken.
Hey, why is it
Cheating,
cheating?
it's using your resources.
Yeah.
The actually saying what's happening here. Slowing down forward.
When you come,
Is that what I'm doing? No, not.
I can't believe how much you guys remember about that. And how unimportant it really is. But I'm glad that you learned something.
I don't know.
Speeding up backward.
oh my god.
Speeding up backward. Funny how you can make, the sound effect makes it. Is this what you mean, Hannah?
Sure is, good sir.
I remember it now because of the sound effect.
I know. That's good.
And,
Oh.
okay. E. See, these aren't too bad. Slowing down forward. It's a velocity time graph. Slowing down forward.
Slow around.
I think this is what Ryan means. Is that what you meant, Ryan?
Oh.
How did you want to come up, tell me how you came up with that?
I get this.
Well,
Or tell the rest of the group?
you have to start at a velocity to slow down.
True enough. So you got to be up here at some number.
Describing whether you're slowing down forward or backwards is kind of
Yeah,
difficult because
exactly.
when you're slowing down, you're going in another direction in a sense. So
I ask you this. Could it be like that?
still right.
No. Wait.
Yes.
No.
Now you're
What is going down? This is
you're not
going back
slowing
up?
down,
If it
you're
goes
just
through?
going straight into a negative velocity.
No, at one point he
It was slowing down until that point, and then it was speeding up back in negative. It's supposed to go straight to the 0 line, so that's not
No
stop.
way.
Did I do it?
Yeah, absolutely.
On the nose. On the nose.
Now, would it be any different if I did, like, what would that be?
That's
That
beautiful.
was
Like, what does that, no, like in words, what does that mean?
That was like real speed, and then it was going down.
Just slowing down at a faster rate, right? And I was going much faster to begin with.
Yeah, it was a really quick stop. It was
Okay.
like the brakes.
Good.
Right quick.
All good. You guys know more than you realize. F. Slowing down backward. Slowing down backward. What does slowing down mean with... if you had to describe this graph here, slowing down forward.
The opposite of that is slowing down backwards.
Yeah, but what does the opposite mean? Like,
On the other side of it.
Please do a reflection on the x-axis.
Where the T is. Yeah.
Please reflect. Thank you.
describe the graph using the word approaching in your sentence.
Approach.
What?
Like, what is That's not a sentence, that's just repeating the word. What would you say the graph is doing?
Approaching. Stop.
Rest. Approaching rest.
Approaching zero, right?
That's how it's
Approaching
down.
zero, it's going down and it's approaching zero. Because when it approaches zero, then it's
It's at rest.
becoming at rest.
It's approaching rest.
Once it gets to there, it's stopped, right? So here it's just approaching zero from
X is
the
approaching.
negative sense. Okay. In question 3, are you guys good back there, you think? More or less? I'm reading faces. It's okay. It's okay. If it's still, we're going to keep coming back to it. It's okay. For the graphs in question 2, produce simple scales ranging from 0 to 5 seconds and 0 to 5 meters per second. Then calculate the following for each graph. So for each one of those, you're supposed to label them with 0s and 5s. And then calculate the acceleration, total displacement, and average velocity. So what they mean is this. They want you to go from 0 to 5 seconds and 0 to 5 meters per second. So 0 here up to 5. So in other words, that's minus 5. Everything is 5. That's what they want. And now they want for each one of those, find the acceleration, total displacement, and average velocity.
Oh, for each of the.
For each of those 6, find acceleration,
No. That's,
total displacement,
you could redraw all of
and
them.
average velocity. You should probably be able to do them in your head, really, because it's just 5s and 0s and 1s, right? I'll give you a couple minutes, then I'll maybe do the first one to get you started. Okay, we are to find the acceleration for this one right here. I'm just going to copy that. Can I do that? I think I can.
Maybe it won't work.
Okay, the first thing we are to find is the acceleration. The acceleration is what of a VT graph, right? How do you find acceleration from a VT graph? Slope. So the slope here is 0. That was easy. 0. What's the second thing we are to find? Displacement. Displacement from a velocity time graph is
Square, the rectangle.
the area. So it's a rectangle, so it's going to be 25, right? And what's the third thing we were supposed to find? Average velocity. To find from a DT graph, go back to the flow chart. To find average velocity from a VT graph, you have to go area over time by finding the displacement first. And so what do? I take that displacement that I just figured out
Over time?
over time, which in this case is 5, or 5 meters per second, which shouldn't be too surprising because it's a constant velocity of 5 meters per second.
Why do I not have that on my phone here?
Well, I wrote it in down here.
I missed that.
You missed that last one? Okay.
So,
Okay, I challenge you to go do B right now. I dare you. I double dog dare you. Do B. Acceleration, displacement, V bar.
Are we all gonna have the displacement like the same, except one couple of positive and a couple of
Could be,
negative?
yeah. Well, when they're flat.
Yeah.
Have you got it?
So we're not flat like that. Oh, no, that makes sense.
If you can do this, it's really, it's about a 45-second job, right? If you can. If you can't, that's fine. There's more to do. We're going to do more practice. Don't worry about it. We'll all get there. What's the acceleration here? Slope of the line. So what's the slope of this line? 0. 0 what? Meters per second squared. What's the displacement? Area. Right? What's the area? Base times height. 5 times minus 5, or minus 25. And what's the average velocity? Minus 25 over 5. unsurprisingly, minus 5 meters per second. Okay, I'm assigning C and D and E and F. There's 4 questions there, 4 graphs. Do those 3 for 4 graphs. The answers are in the back, by the way. So if you're struggling, please feel free to look at those and see if that you can work backwards if you need to. I'll go through those tomorrow.